Hello, this is joint work with Anupam Gupta and Sahil Singla, and I'll talk about bag of tasks scheduling on related machines. So let me begin by defining the problem. So before we go there, let's recall a classical problem in this setting. So this is weighted completion time on related machines. So let's say we're given a set of machines, and the only difference between them is that they have different speeds. So for example, here there are three machines whose speeds are 2, 2, and 1. And then we are given some jobs, and each job can be processed on any machine. Each job has a time at which it arrives. Let's say arrival time is RJ, and it has a processing time PJ, and there is a weight WJ associated with the job. And our so let's say for example a job arrives at time 0, and its size is 10 here. So jobs can be processed on any machine. They can be preempted, migrated, and if you process a job on some machine I, then it gets processed at certain rate, which is the speed of the machine. So that if you just process it on one machine, it will take PJ over SI time, but you can of course distribute it over different machines. For example, here this job has been split into multiple parts, and different parts are being processed in different machines. Of course, I cannot process concurrently on two machines, but anything else is allowed. So as you can see on the first machine, I have processed this job for 2 units. So 4 units of processing has happened on first machine, 4 on second machine, and 2 on the third machine. So total of 10. And so the completion time of job is defined as the time at which it completes minus, in fact, just that. And our goal here is to minimize the weighted completion time. So this is a classical problem. It's well studied. And the setting that we are interested in is the online version where jobs arrive one after another. And also in the non-clairvoyant setting where what is the setting is that we don't know the size of the job until it finishes. So both online and non-clairvoyant. And it is well known, the constant competitive algorithms are known even in this very general online non-clairvoyant setting, but I will not go into that. Um, our interest is in mainly a related problem, which we call a bag of task scheduling. So the setting here is that each job, instead of being just one job, consists of several tasks. So in this picture, for example, the job J consists of three tasks, V1, V2, V3. Now, again, the same scenario applies to each of the tasks. So each task has a size, which could be different for different tasks of the same job. The weight of the job, of course, is associated with the job J only. And now we can, let's say, for example, here there are three tasks with job J, which are shown by different colors. And as you can see, they can be processed concurrently as well. And again, I will say that job J finishes when all of these tasks finish. So the completion time of a job J is a time by which all the jobs finish. And again, we are in the online non-clairvoyant setting, which basically means that I do not know the sizes PV. When a task finishes, I get to know about it. And so when all the tasks finish, that's when I'll say that job J finishes. And again, our objective is to minimize the weighted completion time of the job of all the jobs. So note that WJ is associated with the job J only, but then each task has its own size. Um, and then before I say more about the results we have, let's just see why this would be an interesting setting to look at. So one of the main motivations is that it's a special case of precedence constraint scheduling. So precedence constraint scheduling means that there is some precedence amongst the jobs. And so for example, here, you can think of this is the precedence constraint that job J is a single, you can think of it as a single job of zero size. And it is preceded by all the tasks that belong to this job. And so job J can be started only when all these tasks are finished. So in that sense, the task associated with the job can be thought of as a star precedence relation. And so we don't have a very good understanding of precedence constraint scheduling on related machines. So this is the first step towards this goal. Also, this kind of scheduling problem arises naturally in operating system schedulers, where we can think of a job as consisting of multiple threads, and then when they all finish, then I say that this job has finished. So that's why this is an interesting problem to look at. Let me now state what are our results. Our first result is, okay, so let me just have one small piece of notation. I will say that a machine I is of class K, if it's, so basically what we are doing is that we are rounding the speed of each machine to the nearest power of 2. We can always do that because this will only affect the objective function by a constant amount. And so then K denotes the number of different speed classes. Okay, so it's a class K if its speed lies in the range 2 to the K to 2 to the K plus 1. And now once you do this rounding, then the number of distinct speed that we see, that is K. And the first theorem, we show that even if you have just one job consisting of several tasks, you cannot do better than order K comparative ratio for this. So, and the reason why this happens is that of the non-clairvoyance, because the different tasks may have different sizes. You don't know that. Ideally, you would want to schedule the large task on the faster machine. But since we don't know this, we incur this omega K comparative ratio. And if we were dealing with general precedence constraints, instead of just like a star precedence constraint, then we can even strengthen this lower bound to log n, where n is the number of jobs. The second theorem is the upper bound. We show that ideally would have like to show an order K comparative algorithm, but we can show an order K cube log square K comparative algorithm. We'll like to note that getting a log n comparative algorithm is much easier, but this requires much more work. What is known in these similar settings? Well, if all the machines are identical, then some work is there. So for example, Robert Chavanel and Agarwal and others, they showed that you can get a constant comparative clairvoyant algorithm even when each job is a task. So right now we're thinking of each job as a star, but even if you allow DAGs, then they gave a constant comparative algorithm. This was extended to the non-clairvoyant setting by Garg et al. And so basically exactly the same problem that we look at, but instead of related, if you replace them by identical machines, they gave a constant comparative algorithm for that. Related machines, this seems to be the first work for this problem. Okay, so now what I'll do is I'll describe to you the algorithm. The algorithm is a very natural water filling algorithm, which is also there in the Garg et al. Paper. And then I'll say a few things about the analysis. So let's say the speeds of the machines are arranged in an order of decreasing speeds. Building a schedule may look like a complicated thing because you have to say at which time, on each slot, which job is being processed and so on and so forth. It's much easier to deal with what we call rates. So what we'll do is that at each time t, I will say that, what is the rate at which each task is being processed. So let's take an example. So for example, let's say there are two machines of speeds 8 and 2, and suppose we have 3 tasks. Now, if I say that, and we'll discretize time just for the sake of convenience. So let's say from time t to t plus 1, we can say that task V1 is being processed at rate 7, V2 at rate 2, V3 at time 1. What that means is that during this slot, because in a unit time first machine can do 8 units of processing. So out of that 8, 7 goes to V1, then 1 goes to V2. But the lower down, the second machine again gives like some 1 unit of processing to V2 and 1 unit of processing to V3 because its speed is 2. So note that the blue job has been split across 2 machines, but then there is no concurrent processing of the blue task. Okay, so it's much easier to assign rates like this. And again, it's not hard to show that that if I give you some numbers of some assignment of rates to the tasks, I can convert it into a schedule if the following condition is satisfied. So this condition says that if you look at any set of tasks, okay, suppose there are S tasks, then you add up the total rates that are assigned to them. This sum should not exceed the total speed of the S fastest machines, right? So if you have, let's say 3 jobs here, then the total in this example, the total rates assigned to them is 7 plus 2 plus 1, which is 10, which is at most the total speed of all the machines. If you look at the top 2 machines, then it is 9, which is again less than 8 plus 2. Now, of course, one issue is that you may not have enough machines, right? We're looking at S1 up to S size of S. So what we'll assume is that there are lots of infinite number of supply of 0 speed machines so that we never run out of machines. So if you were thinking of 3 machines, then the top 3 machines will have speed 8 plus 2 plus 0. So that's why this condition makes sense. Okay. So as long as this prefix condition is satisfied for every subset of tasks, then one can build a schedule out of it. Okay, so this is that's why we'll only deal with assigning rates. And one final piece of notation. For a job J and a time T, I'll use TTJ to denote the number of tasks of this job which are active at this time, which are alive at this time. Some tasks may have finished, but it's the remaining ones. And the algorithm now is just a simple rate filling, water filling algorithm. It says that for each time T, I will independently run this algorithm. So it will essentially do some sort of rate increase for each task. So initially all the rates are assigned to 0. And I'll slowly increase the rate of every task, where a task belonging to job J is being raised at the, if weight is higher, then of course its rate will be higher. And in the denominator, I'll divide by the number of alive tasks of this job. So if a job has 10 tasks remaining, its weight is 1, then everybody increases at the rate 1 by 10. And I'll keep on doing this until one of these constraints become tight. When they become tight, then I will freeze these jobs. I will not be able to raise their rates, but I can continue raising the rates of other tasks which are not part of this constraint. So when I finish, then we will have a rate assignment to all the tasks. And then by construction, it follows that all these constraints will be satisfied. So let's take an example. Suppose there are two tasks here, two jobs here. The tasks, job J has a task V1, V2, J prime has task W1, W2, W3. Suppose both of them have weight 1. Then task V1, V2 will increase at rate half, and WIs will increase at rate 1/3. And then you can show that all of them will freeze together, where number of machines will be 5. So 5, of course, there are 3 machines of 0 speed, and these will be the rates. If they have slightly different parameters, suppose J has one task of weight 3, so this increases very rapidly. So what will happen is that this will make the first machine tight very soon. So what will happen is that it will freeze first, V1 will freeze first, and then the WIs will freeze later. So let me now talk a little bit about the analysis, how we analyze this algorithm. So the analysis is basically we write down the natural or the well-known precedence constraint LP relaxation for this problem. And then we consider the dual of this LP relaxation. And then what we show is that you can give some values to these dual variables such that all the conditions are satisfied. Okay. And the objective function that we generate is comparable to the actual weighted flow time of the algorithm. So if we can show this, then we can prove that this algorithm has small comparative ratio. So that's the idea. So instead of writing the LP, the primal LP, it's just easier to, or maybe it doesn't give us much insight, at least now. So we'll just write down the dual LP. So the dual LP looks like this. So just want to draw attention to some of the parameters here. So there are 3 kind of variables: alpha, beta, and delta. So delta JV is essentially saying that, if task B, the contribution, the flow time or the completion time for J is being divided among all the tasks. So every task contributes something towards CJ. Ideally, it should be the last task, but we don't know which one is the last task. So every task will do some contribution towards CJ, and that's what delta JV is. So the total sum of delta JV would be at most WJs. You can think of WJ as 1. So it's saying that delta JVs are being assigned, distributed evenly among all or in some manner among all the tasks. There's a term alpha JVT, which says that what's the contribution? So it should be alpha JVT. So basically, one way of thinking about completion time is that at each time t, you see which are the jobs which are alive then, and you add WJ for that job. So alpha JVT is again saying that it's the responsibility that task B is taking if job J is alive at time t. Okay, and again these things should add up to at most WJ. And then we have a term beta IT, which is a term for machine I8 every time t. It appears as a negative term in the objective function. So the higher you make it, the lower the objective function will be. So you don't want to raise it very high, but then you have this constraint lower down here, which you want to satisfy. Okay. So, I mean, as such, we don't get much insight of it by just looking at it, but let's say a few things about it later on. Okay. So, so this is how it looks like. And just to gain some intuition what is going on, so we'll just consider the special case of, let's say, just one job. And suppose there are n tasks of this job, okay? And now if you look at this constraint, it has a t prime here. So this constraint is written for every t prime and every t, and it should be valid for every t prime bigger than equal to t. So it says that the alpha term on the left hand side should be at most, now this is beta I t here, not t prime, and everything else is in terms of t prime. Okay, remember LTV is the rate assigned to job J to task V at time t. Okay, so as such, it looks sort of a difficult constraint, but I'll just show you what it does here. Okay, so a natural thing to do is that if job J is alive at time t, I just set delta JV, alpha JV t distribute this equally among all the tasks. So you set this equal to 1 by n for everybody. That's a natural thing to do, because at time 0 I don't know how big each task is, so this is the only thing I can do. What do you do with beta IT? Well, beta IT is again, first n machines are being used. You will never use any machine beyond that. So what I'll do is, among the first n machines, I'll define beta IT to be proportional to the speed of that machine. So capital S is the total sum of the n fastest machine. So beta IT for the ith fastest machine would be Si over Sn. For everybody else, it would be 0. And now let's look at the objective function. If you add up, let's say, just look at a fixed time t equals 0 term on both sides. So if you add up to for everybody here, it will be 1 here, it will be 1 here as well, because you have n tasks, each of them is 1 by n, so that's 1. And then again, the speeds are being proportionately neatly distributed. So this will again be 1. So this 1 minus 1 is 0. So you don't get anything of the objective function, but there are standard tricks like speed augmentation by which you can say that you will at time t equals 0, you can make it a constant. So that's not very interesting. What is interesting is that this constraint is satisfied for all machines I. And essentially it follows from the fact that if you have a machine I which is very fast, then you only need to ensure that the rate assigned to the task is at least the average speed, Sn over n. And that again follows easily, because all the tasks are getting equal rates. And so all the n tasks will be processed at speed Sn over n. And if I is bigger than n, it just follows from the fact that all these other machines are very slow, and the rate at which I run these tasks is much bigger than s, or at least bigger than si. Okay, so that's why this works out. But the main point I want to say is that there is this parameter n here, and this n will keep on changing, because as the number of tasks reduce, as more tasks are getting processed, this value n will change. So this kind of dual solution will not work for all times. This is the main caveat. Okay, so more or less this scheme will work as long as the number of tasks don't change much. If they stay at least n by 2, this will work. But the moment they become very small, then this will not work. So that's why this scheme, you may have to redesign these variables again once the number of tasks go below n by 2. So that's why we'll need, like, if you want to just show log n comparative algorithm, then this kind of scheme will work, where you update your dual solution each time the number of tasks associated with the job halves. So this is the picture essentially we want to look at. That this is the left hand side. On the y-axis we have number of tasks, and ml is essentially the number of machines still of first L class, capital ML. Okay, so initially you may have a lot of tasks, and then they'll reduce and so on. Okay, so as time progresses, the number of tasks will reduce. Now if you want to have a k comparative algorithm, what you really want is that when the number of tasks go from ml to ml minus 1, for the entire period you should have one dual solution. We call it an epoch. If you could do that, then the same kind of scheme will give you an order k comparative algorithm. But turns out that that's not possible. But due to some more finesse, what you can show is that each such epoch can be divided into 2 subintervals, so that for each subinterval we can define some sort of consistent dual variable. So I won't be able to say much about the proof, but essentially this is how the proof works. Now, of course, there may not be just one job, there will be many jobs, so you have to keep track of how they freeze during the data assignment process. We call these blocks. Blocks are set of tasks which freeze together. And now for each such blocks, we define these order k epochs, and for each epoch, we can show that one set of dual variables work. And then we combine the whole thing. So I'll close with open problems. So the algorithm is very simple. So there should be a simpler way of showing order k comparative algorithm. We conjecture that it should be order k comparative, but we don't have a way of simplifying the analysis. Now, instead of a star graph, as we say, tasks can be thought of as a star graph. What if we had a general tag? So each job was a general tag of there could be arbitrary precedence constraints among the tasks of a job. So for that, we have a lower bound of log n, but can we get a log n comparative algorithm? That will also be good to have. And finally, all this was only in the setting of non-Clairvoyant scheduling. What if we have the Clairvoyant setting? What if I tell you what the size of each task is? Can we get a better algorithm? Thank you. I'll stop here.